Our final exam is on Wednesday. Okay? So I've already written one version of it. Now I'm going to go through it again this weekend and change things that I don't like. All right, so we are going to take some notes. Everybody should have that note sheet out in front of you, if you could, please. If you need there's a case study. I'll talk about that in a little bit. If you need a pencil, I have writing utensils right over there. Let's do this. Ladies in the front, if you jeopardize each other's success, this is going to be irritating. Don't jeopardize each other's success. Billy, can we see the screen okay? Thanks. We're going to talk about earthquakes today, and I'm going to go kind of fast because I want to make sure that we have time to talk about things. Don't write anything down yet. Where are most earthquakes located? Did we find out? Matt, do you need a pencil, bud?
Nope.
I know, but do you need a pencil, bud? Nope. Okay. Where are they located? How many of you agree? Boundaries? Just like volcanoes. Global distribution of earthquakes are here, but I like this picture better. Each one of those black dots shows an earthquake. Look at how many are around the plate boundaries. In particular, do you notice any particular boundaries where we seem to see the most earthquakes at? Turn with your pair share partners and talk that out. Ready, set, go. 5 seconds.
5, 4, 3, 2, 1, and we are done.
What do we think these are?
Earthquake.
That's right, but what kind of boundary?
Transform.
Not transform.
Convergent.
Convergent, yeah. We see a lot at transform boundaries, that is true. But we see a lot at the ring of fire over here, and the other part of the ring of fire is here. This is all convergent boundary. Yeah, and then the second most is definitely by transform. All right, so let's go ahead and go through this. Everything's underlined for you. Right, are you distracting Peyton? Most common along plate boundaries. Do you need a pencil, bud?
No.
Pick it up and write this down. Transform boundaries are boundaries that slide past each other. So we're doing a little review here to get ready for our exam on Wednesday. Example of a transform boundary would be your North American plate and your Caribbean plate. When we watched the movie the other day, that was the Haitian earthquake. Devastating. So sad. Not great building materials in that earthquake or building styles, and the houses just pancaked one on top of another. Another is your convergent boundaries. This is where they come together. Do me a favor, next to this somewhere, can you please write the words mega thrust? These are where our mega thrust earthquakes are located. These are the most powerful earthquakes in the world, in the history of humanity, have been at convergent boundaries, and they're called megathrusts. Anywhere that you have subducting plates, you're going to get these major earthquakes that happen. An example would be when the Nazca plate and the South American plate come together. And again, in our video, that was the Chilean earthquake. And we saw that one part of the coastline that had jumped up, I think, by 2 to 3 meters. Crazy! And then our last one is divergent boundaries, moving apart. Very few earthquakes happen here. So if you were going to rank them, right, convergent is going to be the most powerful earthquakes we have. Divergent, not very many earthquakes. Ready for the weekend? Ready?
Yeah.
Okay. You too, man. Laura, are we good? Yeah. All right, there's a picture of our beautiful plates. We've got some pictures here of the North American plate. This is the Caribbean plate, and we can see that there's a strike slip here, you know, and a convergence boundary here. I mean, and Haiti's earthquake was right there. And they said that, you know, sometimes when a little slip happens, the stress just continues down. And so, yes, stress was released here, but then it builds up somewhere down the road. So, you know, when one earthquake strikes, if you're in an earthquake area, you got to worry maybe there's going to be more coming. All right, so let's talk about focus and epicenter. Focus is the place under the ground that the actual rupture of the rock happens. It's the location of the earthquake. It would be right here in this picture. Underground, this is where the break happened. The epicenter is the location right above it on the crust. Okay, so or right above it, like on the land, on the surface of the land. So if you were in a, I'll just use this. If you were in a city located at the epicenter, you would have probably more damage than if you were a city farther from the epicenter, right? The epicenter is the location right above where the earthquake happened. Justin, this is yours. I found this on the ground the other day. Focus in the ground. It's the fracture. Epicenter right above it. All right, how do they form? Rocks have a limit to how much stress they can absorb, just like students do. And then you break, just like rocks do. So, when you build up stress in a rock, like me building up stress in this stick, it can only hold so much stress, and then what happens?
It breaks.
It breaks, and it scares you. So it breaks. That would be like an earthquake. Same thing happens with a rubber band. If I load this rubber band with stress, I am loading it with potential energy, and then if I let it go, that energy turns into what kind of energy? Kinetic energy, the energy to do work. Let's see if this rubber band can do work on those papers. It did. It moved the papers. So my potential energy was turned into kinetic energy. So that's what happens during an earthquake. We're building up stress in the rocks, and then when the rocks break, that stress is released through the rocks. When rocks are strained beyond their limit, they break at the focus, and they grind past each other. This then releases huge amounts of energy. It travels through the ground, and that's the ground quaking, the earthquake. I have an earache. Did any of you get earaches when you were kids? Like, I mean, little, I know you're kids, but like little kids. Earaches, ear infection, do you know what I'm talking about? Oh. Oops, sorry. Are we good? Justin? Okay. This is just a picture showing the layers of the rock, and if you compress them for a long amount of time, they will bend and distort, but in that time period, I mean, imagine if there's areas of weakness, you're going to get like a little break or a fracture and a rumble. That's going to be an earthquake. All right. Let's look at the different types of faults that can happen. Peyton, zip it. These faults I'm going to put on the exam. Okay. This is one, and I want you to look at the different layers, and I also want you to look, in each one of these, we're going to have a little stream. In this area, you can see the stream has been separated because one of these is moved in this direction, one's moved back. So they're kind of sliding like this. What kind of boundary is that?
Transform.
Yeah, so let's go ahead and write down first, strike slip fault next to the big picture. Next to the big picture, you're going to write strike slip fault. And I promise you that we'll have pictures just like this on the exam. It's a strike slip fault. Strike slip faults, and you can see here that all of the movement is just what's called horizontal. There's no vertical uplift of the land. It's all horizontal. So here's a picture in situ. This is actually a strike slip fault in situation, in the location. And the land just kind of moves, but there's no uplift of motion. Look at how that land just got ripped. This usually, occurs at a transform boundary. And the motion of the plates, as I said, is horizontal and opposite in direction. It would be so cool to see something like that after the fact, you know.
You just steal the grass and put it on your lawn.
I guess, yeah, the sod is kind of ripped out. I mean, really scary, like if there are, you know, water pipes running through that area, I mean, forget about it. Everything's gotta be dug up, gas pipes, you know, everything. Are we good, darlings? All right, this results from what's called shearing forces. So the forces here, we say the land has been sheared, kind of like your kitchen shears, where one's going in one direction, the other one's going in the other direction. That's why these are called shears. Maybe they're not anymore. Has anybody ever heard like your grandma or grandpa say, get a pair of shears? No?
Skizzers.
Skizzers? Another word for scissors are shears. Got that same motion. All right, next type of fault. This, you can notice that we've got our little river. In this kind of situation, we probably have a waterfall that would start. In this case, we've got two different sections of the land, and one of them is called the footwall. Let's see if you can figure out which one is footwall and which one is the headwall or the header. So I'm going to label one A and one B. With your pair share partners, let's see if you can just figure out which one is the footwall and which one is the headwall. 5, 4, 3, 2, 1. Okay, any guesses? Just for fun. Yep.
A would be the head wall.
A is actually the footwall, and this is how I remember. The footwall, because for me it looks like a little blocky foot, you know, shoe or something. You put your little foot in there. There's my toes. That's the footwall. Now, the reason they call it the footwall and the headwall is very interesting to me, and because it's interesting to me, I'm going to share it with you. A long time ago, when miners would look for gold or metals or whatever, they would look for natural faults already there. These are cracks in the earth that was easier to get into. They would walk along the footwall. Notice how it's slanted like this. So this is where they would be walking on. They would hang their lanterns on the ledge that would be over them, and that would be the hanging wall or the head wall. Okay, so that's the hanging wall. You'd hang your lantern, watch your head, and this is the footwall. This is where you're walking in the mine. We don't care about that. All right, call this a normal fault though. This is a normal fault. I don't know why this is a normal fault. I don't know if this is the most frequent fault. I don't know, but it's a normal fault. Write that next to the picture. Normal fault, where the head wall or the hanging wall falls. This happens because the land is being pulled apart. There's a picture of, you can see this is what's called a fault scarp. Fault meaning break in the rock, and it's that scarp or that edge that's up. There's another really good clear picture of it. Happens at a divergent boundary. Land's being ripped apart. One side, that hanging wall, drops down relative or compared to the other. And this is what's called tensional forces. Think about like you're pulling or playing tug of war with the land. You're creating tension on the land, tugging it apart. The land is moving in this direction and this direction if you need to add arrows to help you out with that. And what you're going to have typically is you're going to have a big fault block mountains on one side, fault block mountains on the other side, and a deep valley in between, where the land in between is just dropping down. I think it's called a graben or a graben or something. Good? Tensional forces at a normal fault. This is just saying Nevada had an earthquake in 1954, so the land was being, pulled apart, and this thing just dropped down. All right, the last one. What do we notice about this compared to the last one we looked at? Yeah. Yeah, it's opposite of the other one, right? Yeah. So they call this a reverse fault. So just remember it's reverse of the normal fault. In this one, you're right. the hanging wall gets popped up and the foot wall falls down. So if the other one was tensional force, what kind of force do you think this is on the land? Yeah, so in this case, the land is being squeezed together.
So convergent.
Yeah, these are convergent boundaries. So it happens at areas where the land is coming together or being compressed. One side, the hanging wall, is thrust up and over. The reason they say up and over, here's a really good picture of it. I know this isn't land, but it's a glacier. And so the glacier was being squeezed in such a way so that when it broke, this was, popped up, and you can kind of see that it's tilted out towards her like that. It's a really sharp kind of fault scarp. It looks cool. It's like what? Yeah. So this is due to compressional forces pushing together of the land. Good? Am I in your way?
No.
Am I going too fast? I'm going to take a drink. It's mint tea with honey. You okay, William? You tired? I think we all need a little break. I've heard there's quite a lot of sickness going around lately. I know, right? Just in time for it. All right, let's go ahead and look at the other side of the paper. We're now going to be talking about the waves that happen in an earthquake. Does anybody have any 2-liter bottles at home? Nobody drinks 2-liter bottles of anything anymore. Does anybody have? Do you?
2-liter bottle.
I'd love it. Any 2-liter bottles you have at home, I'd love to have. If you're willing to donate. If not, then I'm okay with that. I know what it's like to hold on to that 5 cents. Then you get back. Seriously, I'm not joking.
We usually go there once in a blue moon and get maybe $2-3 out.
Okay, well, that's a lot of soda bottles.
Yeah.
All right.
But we've recently just.
Earthquakes produce several different kinds of seismic waves. What is a seismic wave? A sudden release of energy or vibrations traveling through the ground. We have the primary wave. That's the first one, or primary. We have the secondary wave comes next. That's the second wave to come across an area. So far, easy to remember, right? Primary comes first, secondary comes second. I love earth science. Surface waves travel on the surface. That's the last wave to come through. So if you want to do some numbers to help you out, 1, 2, 3. If you remember from the video yesterday, the P wave, or the primary wave, is the one that comes through with the least amount of damage. It travels really fast, and we have anywhere from a few seconds to a minute, depending on how far away the focus or the rupture was, in order to warn us that these two destructive waves are coming. I mean, that would be great, right? Your phone goes beep, 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 earthquake on its way. Seek shelter. I'd love that. Here, it would be pointless. Each wave travels through the rock at different speeds and causes different kinds of motion. Write that down. Oops, sorry, back up. I thought there was a picture. Sorry. Does anybody see Alex during the day after this class?
Yeah.
Could you just let them know that these are posted online? They might have went home sick, I don't know, but if you see them. Good? All right, let's talk about them. Primary wave, or the P wave, also known as compression waves. Ooh, this sounds really familiar since the beginning of the year. This is the first to reach a location away from the focus. Remember, the focus is the area of rupture under the earth. It's where the rock broke. It travels out fast in all directions. It's very similar to sound waves. It's a longitudinal wave. This wave can move through solids, liquids, and gases. So this wave is really good for us to figure out. This is how we figured out what the inside of the earth looked like. Because some of the inside of the earth is kind of liquidy, and so we were able to use this in order to figure out what the inside looked like. Because even though it can move through all solids, liquids, and gases, it will change speeds depending on if it's moving through a solid or a liquid. It will go faster through solids and slower through liquids. This is what it looks like, a compressional wave. So it kind of does this kind of thing as it's moving, like a sound wave. You know, when we, if you remember that, in the beginning of the year. Secondary waves, S waves, also known as shear waves, because the land moves up and down like this. So it's shearing the land. If you had a pipe traveling, oh, let's do that. So if this was a pipe traveling through the land and I move up, right, and one part goes down, this pipe is just going to snap in half. It's not going to move like this. It's just going to snap right there. The rock moves at right angles to the direction that they move. It can only travel through solids, which is why we knew that part of the interior of the earth must be liquidy, because we could not get or detect these waves, these S waves, at certain parts of the world on the other sides of the world because they weren't coming through. So we're like, gosh, it must have traveled through some sort of liquid thing in the earth because it can't, so it stopped. So when they say that they're shear waves, it just means the land goes up and down like this. So you're shearing anything. Moves right angles, so the energy goes this way, and the land goes up and down. This is like your transverse wave, if you remember transverse waves from the beginning of the year. Our surface waves, these are funky. These are the most destructive. They are the last to arrive to a location, thank goodness. So if you have not left the building, get out before these come. One creates an up and down rolling motion. That's called the Raleigh wave. The other one shakes the ground side to side. I think that's called the love wave. I think they were named after the people that discovered them. So at the same time, both these waves are happening. The best way for me to describe this is you're in the back of a pickup truck, standing up in the bed of a pickup, and somebody is driving down a road that goes like this as they're doing this with the steering wheel, right? So you're trying to like keep yourself steady. Yep, yep. So this one is going to take down the buildings that haven't already been taken down. Now, it's going to be worse if the underlying geology is not bedrock, right? If you've got loose underlying geology, then everything's going to kind of get all liquidy and, you know, build your house on something solid. Liquefaction. There's a question on the exam. All right, so we're going to pair share. I'm going to show you an animation, and I want you to think of the speed of the wave travel, the damage caused, what type of waves are they, and how does the energy move compared to the land? All right, you ready? Everybody has to be looking because once I start the animation, it's going to start. Justin, eyes up here. Good? Okay. Are we all good? Ready, set, go? And we start. Which one hit first? B wave, write that down. Which one hit second? Which one causes the most damage?
Surface.
For sure, the surface wave. That poor house. All day long it's had to go through this. I don't really know what the other questions are, I'm sorry. What are the other questions, darlings? Oh, my glasses on today. Oh, which one are longitudinal waves? Kendall, put your phone away. Which one are longitudinal waves? Which waves go like this?
P
The P waves are longitudinal waves. That's a longitudinal wave. And then which ones are transverse waves? S wave and surface wave. The S wave and the surface wave are both transverse waves, meaning they have a crest and a trough. Crest and trough. Does that kind of sound like I'm speaking words that you might have remembered from way back when? Crests and troughs? You pay attention. I meant to give that to you the other day. All right, so let's go ahead and draw a picture of these, because part of what you have to do is draw a picture. So the first one, under P waves, I would kind of draw them the way we did when we were doing longitudinal waves. I'm going to turn this light on so that it shows up a little bit better on my video. Longitudinal waves have areas of compression and rarefaction. So if we're going to go ahead and draw those, I would do an area that as it's traveling through, you can kind of see that it's compressed. So in this case, the material moves this way and the energy moves down the line. That's what it's asking you to do for a drawing. Material's moving back and forth, so there's no vertical up and down motion of the land. So there's not a lot of damage as the earthquake moves through. And depending if it's solid rock, these particles are going to be much closer to each other in solid rock, and so it's going to move through really quick. If these particles are farther away from each other, like in sand, you're going to get much more shaking of the ground. So that is your longitudinal or your P wave. So this would be the P wave drawing. The surface, S wave is going to be your crests and your troughs. In this case, the land goes up and down, that's the movement, and the energy is moving down the line. So this is what you would draw for S wave. S wave or secondary wave, the second wave on site. The last one's kind of hard to draw. Imagine, if you will, you've got the transverse wave like this, and then you've got like a sidewinder sort of sideways wave like this. So we've got the wave moving sideways, but also another wave moving up and down, and the energy is moving down the line. That's the best way that I can draw a surface wave. So I can't imagine being in a situation where I have got the land moving beneath me like that, if I had to save and, keep all of you safe. I would do my best. I'd be like, get on the ground, get underneath the desks, because these desks are sturdy, and, you have tiles and stuff falling on you, but get under the ground, or get under the tables. Are we good on that? Good? Jose, get off your phone. All right, we are going to talk about your case study. This is your final project of this unit. I want to let you know again, we have our final exam on Wednesday. You do get to use your notes. Your final exam is going to be on plate boundaries, plate tectonics. It is going to be on volcanoes and earthquakes. So it's everything on Unit 5. You can't wait? I like that. This is going to be your case study. I'm going to give everybody a rubric so that you know exactly what you're going to be graded on. Don't put away this rubric, because I want you to write case study site on it once you pick which case study you want. You may not work with a partner. You are going to create your own case study. Actually, can you just take one of these and pass it down? And then just kind of keep passing them out. Can you give to the people behind you first? And then I'll collect them on the end. All right. So when is this due by? By Thursday, end of class Thursday. Thank you, Rebecca. End of class Thursday. Jose, I'll just come get them from you later, or you give them to me. All right, let's look at what it is you're doing. Directions for Google Slides. You're going to open up the Google slide, make a copy. All right, I've showed you where that is. This will save a copy to your Google Drive. So you're only view only. So don't do one of those things, Miss McGrain, I can't, blah, blah, blah. You can open it, but you just have to make a copy of it and save it to your Google Drive. Change the name to reflect your site name and your period number, okay? Or you can say case study, you know, McGrain if you want, or science, and then the period number. Remember to keep track, oh, I guess I want your, yeah. Remember to keep track of your sources on the last slide. So you're going to need to set your sources. You're going to, when you're done, click share and type in, oh, you're not doing that because you're not, this year we decided as teachers, we're not allowing you to work with partners. Why do you think we're saying no partners this year? What? Not if you're with your partner, right? If you're with your partner, you don't cheat. Right. So what we were finding was one person was doing all the work, maybe because they're like you really want to work hard and get the best grade possible, and somebody else is like, nah, whatever, I'm fine with a D as long as I'm passing. So you would do all the work and they would do nothing. Could be something like that, right? Or somebody would say, hey, I did my half, Mrs. McGrain, but William, sorry, not you, you never, might not have done anything, and then your grade suffers because of it. So we're just like, everybody does their own. Obviously, you're going to delete this slide when you're done. I don't want this as part of your presentation to me. And you're not presenting in front of anybody. You're just going to hand them, share them with me. All right, this was a task responsibility matrix just to kind of like keep track of things. Again, we are not presenting, so don't worry about that. Okay, here's your case study sites. You can pick from one of these things. That's what it is, but not everybody can do the same thing. So I'm only allowing 3 of each. And if I know that you're like, oh yeah, you're doing that, you and you cannot do the same site.
Us too.
We're not doing it. I'm just saying, you know, like if it's your best friend, right? Like Kendall and Maya, you're not going to be doing the same site. You see what I'm saying? You're going to pick something different. Which one do you want?
I want the Mount Earth.
Okay, so you want the Mount what?
I want number 6.
You want number 6. Okay, so number 6 is gone. Write that one on your thing.
I want 4.
Hey.
I want
Number 4.
Oh my God.
Okay, so number 4's got 1 of them.
I want 4.
You want 4 also. So 4's got 2 of them. How about we just do this down the road?
Well,
2. Write that down on your case study sheet then. Yes.
3.
3.
Wait, actually, I changed it 3.
Sorry, you already chose one.
Okay.
It's not fair. In the middle. 1. Write that down. Rebecca. 11. We're going to have plenty, y'all. Kendall. 1. Let's go over here. Will. Yeah. 3, please. Maya, did you already pick?
3.
3. Okay, so now Mount St. Helens is done. Yeah.
2.
2. Lauren.
2.
2. Okay, so now San Francisco earthquake done. Jose. 4. That one's done. Braden.
11.
Sure, you bet. They're all good, y'all. Ethan. 10. Kylie. 11. Mount Everest is done. Billy. Which one, huh?
I just said 5.
5? That's a good one. Yep.
Number 8.
Number 11. Number 11's done, bud.
No, I think number 8.
Number 8, ooh, Krakatoa. Yeah. 10? 10.
Mine's the oldest. We're not that, is it?
Number 9.
Which one's the easiest?
Any others? Did everybody get one? Write it down on your paper. Write it down on your paper, and then what I'm going to do is I'm going to show you what you're going to have to do. Are we good? Everybody write it down?
I should have picked.
Are we good? Okay, nobody's, yes? No one's saying stop, stop? All right, so your presentation. This is kind of what you're going to do. You're going to have a slide for each. Notice I've given you a slide for each. First case study, blah, blah, blah. Put it in the title, right? And then this is going to be kind of like the slide for this, slide for that. So all your slides are there. You just have to kind of fill them in. I'm telling you what I want on each one in this area. I'm going to show you where to go. This is a link for Plates on the Move. This is where you start. This is going to give you information. Watch this video first. If you want information down here, right? Watch, read, play these so that you can see how subduction moves. Read through this. If you want more power in plate tectonics, because a big thing of this is getting information, definitely go ahead and cite this. This is from, I think, the American Museum something, something. And then when you're done, you will play this game. On here, it will bring up a big map. You will look for your event. Listen to me, please, Braden. You will look for your event on the map. Click on that, and that will give you lots of information that will help you with what you're doing, okay? Go ahead. I'll show you what it looks like. So if you do this, right, these are the different locations for the events that I have given you. So what you're going to do is search for them, and then you pull them up, and it'll give you information. If you want to see the plate names, you can do that. Because part of it is like, what plates are these on? Questions? Comments? Lots of information here for you to be successful. If you want more information on volcanoes, if you want more information on earthquakes, all of that is here, and also at the bottom here. Okay, so if you want more information. And then you just kind of fill in all of the slides. We're excited. And then share it with me. If you click on here, you'll have Mrs. McGrain's email. It'll email right to me. Good? Do we know what we're doing? You can get started on it this weekend, or don't. You're going to have Tuesday to work on it in class. Wednesday is our exam. Thursday to work on it in class. Due by the end of class on Thursday.
How much is it worth?
15 points. It's on your rubric.
I'll do this.
Billy, would you mind shutting this off?
15.5.